All right, guys, this is your second piece of notes that you've had to do on your own at home. So just like the previous night, what you're going to do is you're going to complete this along with my video. And when you come into class tomorrow, we're going to immediately begin practicing these skills. So the skills that we're going to cover in this lesson is we're going to be able to determine intervals over which a function is either increasing or decreasing. And determining increasing or decreasing is not going to be difficult for us. It's literally as simple as the function is increasing here, the function is decreasing here. But it's going to be identifying those intervals that we're going to really need to talk about. And then we're going to be able to calculate something called an average rate of change over a function when you're given an interval as well. So the first thing I want to do is point out that this is a function. We're going to call it the function f of x. And it is a function because it passes that vertical line test. Remember, if I drew vertical lines all over this graph, there's no vertical line that I could draw where I would intersect with this function more than once. And I really want to draw your attention to this point on the graph because this vertical line here, I'm drawing it at x equals 6, looks like it intersects with the function twice, but it doesn't. It does intersect with the function at this point 6, -3. That is a point. But this is not a point. There is no 6, 2. That is not a point on the graph. And the reason that is because of this hole. There's a hole in the graph right there, and it's showing that there is a discontinuity and a jump from here to here. So this is the point when x equals 6. The output would be -3. Okay, so it passes the vertical line test, and it's got a lot of stuff going on. There are some linear parts to this function. There are some parts that kind of look like a parabola or like they might be cubic, but really we don't have any information other than that this is what it looks like, and that's all we really need. So the first question says, over which intervals or interval does f of x appear to be concave up or concave down? Just a real brief review of concavity over here. Concave up is when a parabola or a section of a cubic or any other polynomial looks like this. It's facing upward, it's opening upward, all right? And concave down is just the opposite. It's when we're opening downward. All right, so what we want to know is, where is this function concave up or down? The first thing I want to point out is that lines do not have concavity because they aren't bending at all. They're not opening upward, they're not opening downward, they're just linear. So we don't have any concavity here. But right here is where we begin to see some concavity. All right, so starting when x equals -2, it looks like we're opening downward. This is concave down. So what I'm going to do is I'm going to say we do have an interval that is concave down. Starting at -2, when we're talking about our x values, remember. So when x is greater than -2, so starting at -2, when it's greater than, it's concave down. And it stops being concave down right about here. Because you'll notice right at that point, it turns and opens so that it's upward. So that's kind of a difficult point to identify, but that's when the x value is 3. So when the x value is 3, it is no longer concave down. So we have that interval from -2 to 3. And there's a quick way to write this that you're going to see your intervals from now on. We may have talked about it before, but just to concretely cover this, I could also write that interval this way. That means the same thing when I'm talking about an interval. And I know that that looks exactly like a point, but we're talking about an interval, right? The question said, over which interval, and I gave this. So a point would not make sense within this context. This is another way to write that. Notice that this does not say less than or equal to. It just says less than. That's why we used a parenthesis here. And the same thing here, it just says less than. That's why we're using a parenthesis. All right? We'll talk about what happens when it's less than or equal to when we come to an example like that. All right, so then it looks like we have concave up, starting at 3, and then x ceases to be concave up when we get to 6. 6 is the spot where we're no longer concave up. And we can rewrite that just like this. It's a much faster notation for an interval, and you'll start to see intervals given to you like that. All right, so concavity, not something, again, that's a huge part of the Algebra 2 curriculum, but something that you're going to see a lot later in mathematics, and I do want you to be familiar with concavity. Okay, the next question. Does f of x have any roots or y-intercepts or critical values? Now, we don't even need to have this word roots here. That's kind of redundant because it says critical values, and roots are critical values. So we could just say, does f of x have any y-intercepts or critical values? So when we're talking about critical values, what we're talking about are roots, and we're also talking about maximums and minimums, right? So I'm just going to write down that those are the things we have to fill in real quick. Okay, so these are the pieces of information we need from this graph. We'll start with roots. Roots are pretty basic. They're easy to find. It's any spot where we've intersected with the x-axis. So that's a root, and this is a root over here. Don't forget that one. Okay, so what are those roots? Well, when we're talking about roots, just like when we're talking about y-intercepts, we really can just give the x-coordinate because we know that the y-coordinate is 0. So we do have a real root when x equals -5. It looks like we've got one when x equals negative maybe 1.5. That could be this one here. And one when x is equal to 8. So those are some critical values. Those are roots of this function. Maximum points. I see 3 maximum points. I see a maximum over here. That would be a local maximum. I see a maximum again over here. It's a local maximum and a root. And then I see an absolute maximum here. That would be an absolute maximum because it's the absolute highest part of this graph. It's the largest value that any of our points have. So let's fill in those points as maximums. All right. And then we've got some minimums. But really there's only one minimum point we can record. A key thing here is that these points here are all minimums, but we can't say they're local minimums because in relation to each other, they're all the same height. Remember, we've got an infinite number of points that exist right here. So we can't use these. We can use this point. That is a local and absolute minimum. So we'll use that for our minimum point. That would be the point 6, -3. Okay, and lastly, we do have our y-intercept, which is clearly y equals 5. It's an easy one. All right, the next step. Over which interval or intervals is x increasing or decreasing? Sorry, f of x. Okay, the interval where f of x is increasing looks like we could go with either here, that's one of them, and here is another one. So we've got some increasing happening there. So when we're talking about intervals, remember we only care about the domain. We only care about x values. So let's record our intervals of increase. Our first interval of increase, let's see, we're decreasing. This is just a 0 slope here. And then it begins to increase at -2. So it looks like our interval begins at -2, and then it stops increasing at 2. Because you'll notice as we travel along the function, we get to 2, it stops increasing, and then it begins to decrease. So that'll be an interval of decrease, but we'll get to that in a minute. Then it starts increasing again. So this is another interval of increase between when x equals 6 and x equals 8. So we'll put that for another interval of increase. And we also have some intervals of decrease. It looks like the function is decreasing at -7 and from -7 to -4. So that's one interval of decrease. And then we talked about how it increases again up here, but then it starts decreasing again when x is equal to 2, and it stops decreasing when x is equal to 6. So we'll say that our last interval of decrease is when x is equal to 2 to when x is equal to 6. All right. Looks like, again, I overestimated the amount of stuff that I was going to be able to fit into this video, and I don't want it to go over 10 minutes. So here's what we're going to do. This bottom part, which is really important, these last two, we are going to finish in class. I'd like you to do this piece here before you come. I want you to guess at which interval you think f of x is increasing the most. Come to class with that, And then tomorrow we will talk about average rate of change because I'm going to have to give you a formula. All right? So good luck with that, guys, and I will see you all tomorrow.